All right, in this video, we're going to focus on analyzing embankments over soft compressible soil using a program like Slide to do our slope stability calculation. So I'm sketching that same kind of levee that we've been analyzing for all of the videos so far. And what I've done is put a piezo line here across the surface. So I'm assuming that the groundwater table was right at the surface before we constructed this levee. And the trick here is that there are quite a few different ways of analyzing this problem, right? So let's talk about the simplest way. That would be to do a total stress analysis. And what you would do is compute the shear strength beneath the levee at whatever time you're interested in analyzing it. So, maybe you could construct the entire embankment and check the factor of safety first, in which case you would use the same shear strength everywhere, right? Maybe it would be a function of depth, but it would not be a function of horizontal position, because at the time you've constructed the levee, no consolidation has happened yet. It's undrained, it hasn't started settling and getting stronger. If you build one stage, let's say, this is 4 meters high. Let's say you build 1 meter first. Well, now maybe you're going to have a higher shear strength under this region before you add the next stage, because you've waited for consolidation to happen after stage 1 and before stage 2. So we could do something like sketch a material boundary, like this. I'll go to there, and then, this material is going to be under the weight of that little triangular load, and then maybe you'd have a region in the middle that's even a little bit stronger. That's perfectly fine. You can do that. I'm going to just undo. I'm not going to do that. What I'm going to do is show you how to use the Shansep material to automatically do strength normalization, because I think that it's a better way of solving this problem. Just because underneath this little triangular load, actually the change in consolidation stress is very low near the toe and quite a bit higher beneath the crest. So you'd have to have something that varies quite a bit. You might have to divide this little region into 3 or 4 subregions, each with progressively higher effective stress as you move left to right. So let me do one thing. I'm going to go project settings. I have to turn off this advanced feature that I want to illustrate later. All right, so here we've got material properties, Shansep. So if you come down here, more Coulomb's way at the top, Shansep's way at the bottom. And first I'll say Shansep is actually a method for performing laboratory tests in order to analyze soil strength. This is really just strength normalization, which is part of Shansep, but Shansep is more than that. And strength normalization predates Shansep. So anyway, what we're doing here is that the shear strength is equal to sigma v prime times s times OCR raised to the m power. And then they give us the option of adding this little a term. And this is kind of nice. I was talking in the previous lecture about how usually we put a little layer of sand on there because we need some effective stress at the top. Well, the reason is that if you set sigma v prime equals 0 and a is equal to 0, then the undrained strength is 0 right at the surface as well. And if you add any load to that, it's going to fail, right? There's not going to be any strength. In real life, clay usually does have some strength right at the surface, and so we can now use this A parameter to kind of represent that. So if you go and push a cone, you can get undrained strength with depth. You can probably calibrate what this A parameter is. So here A is 5 kPa. I'm going to put in 0.2 for the strength ratio and 0.8 for the M factor up here. And then we have the option of defining the over-consolidation ratio. So I'm going to come in here and make it 1. Let's make it like 1.2. It's pretty unusual to actually have an undrained OCR of 1 because there's secondary compression that induces over-consolidation, even if there hasn't been any mechanical load on the clay in the past. So 1.2. Okay, and then with the Shansep method, we do now need to combine some effective stress concepts. So the reason I drew that piezo line in there is that we need to know the effective stress here, vertical effective stress, in order to calculate the undrained strength. So even though we're doing a total stress analysis, we still have to have a water surface in there so that we know what the effective stress is in order to compute the strength. So I'm going to push OK. We're ready to go here. And then I'm going to do calculate. I've got my grid search set up here. Oh, and this other material, material 2, is a more Coulomb material with 1 kPa cohesion and 35-degree friction angle. So, you know, a sandy material. And I'm not putting any water surface on that because it's above the water table anyway. So let's go ahead and calculate. It turns out that there's a problem with this analysis that I'll try and explain. It seems pretty intuitive to do it this way, actually, but it turns out that there is a problem. Okay, so here's our factor of safety is 1.3, right? And this is a problem where I'm still having some statistics. Let me turn that off. Okay, let's turn that off because we don't need to do reliability analysis. It's just left over from the previous lecture where I talked about that. Okay, so we get a factor of safety. Close this and try it again. Reload here. Factor of safety is 1.292. I would say that that's probably fine, right? Like for most embankments, we would decide, oh, this is no problem. It's 1.3 right now, but it's going to increase over time as consolidation happens. Well, let's take a look at the undrained strength. Here's a property viewer window, and this is showing shear strength as a function of position beneath the levee. It's showing shear strength not of the levee material, but just of the clay. And what we see is that there's a different strength now over here in the free field than there is beneath the levee. We're already getting a pretty high strength right beneath the center of the levee, and recall the failure mechanism goes right through here, and a lower strength out here in the free field. So the reason why this is happening is it makes perfect sense, but it's a little bit counterintuitive at first to think about. So let me go back to the modeler. Okay, if you have a failure mechanism here, right, the clay right beneath there, let's say you have a slice coming down. Maybe it's better to stick with this one. We can turn on the slices. So let's talk about like what happens if you go to a slice right here. Well, you've got all this weight of the levee material acting on top of it. So when it calculates the effective stress, it's using this piezo line to get pore pressure, but it's including the weight of that fill as part of the effective stress. So even though that you know, what we're not capturing here is the fact that the fill has been placed, but the clay has not yet consolidated under that weight. This particular analysis has assumed that it's fully consolidated. So this would be like the factor of safety at time equals infinity, not at time equals 0, right after we've built the embankment. So there is a way to tell the program to assume that the pore pressures are not, that there's excess pore pressure in here. And the way that you do that is to go to Analysis, Project Settings, Groundwater, and now we're going to click on the Advanced tab and do this excess pore pressure option. And we can now tell the computer program that there can be excess pore pressure induced either by external loading, so if you put a surface pressure, that might induce excess pore pressure, or from adding material like soil on top. So what we'll do now is go back to Material Properties. And here's the piezometric line 1, H sub u is 1, and we're going to do the B-bar method, right? And B-bar is 1. That means that any change in vertical total stress is equal to the change in pore pressure. So there's no change in effective stress if B-bar is 1. We're loading the soil, but its strength is not immediately changing. And of course, there can be some shear-induced pore pressure that can alter B-bar, but if it's a B-bar of 1 would be like what you would get for infinite loaded area, like for one-dimensional consolidation, where there's change in vertical and horizontal stress that are the same, but no shear stresses or anything that might cause shear-induced pore pressure. Then there's this button here too, material weight creates excess pore pressure. And this one is a little bit confusing to think about, but basically what this is saying is that the weight of this clay material, I'm going to change the name to be clay so that it's clear, does the weight of this clay material create excess pore pressure? And in this case, it doesn't. We're assuming that the clay was there and it became normally consolidated under its own weight. So the weight of the clay is not what's creating the excess pore pressure, it's the weight of the sandy fill. So let's go to material 2. We'll call this one sand fill. And now we have this box checked, right? Material weight creates excess pore pressure. So what we're saying is when we put that fill on, that's going to induce excess pore pressure in the clay, and it won't be consolidated yet, right? So we'll be doing an undrained loading condition rather than the final drained loading condition. Notice that even though this material creates excess pore pressure, we're not using a piezo line or assigning a B-bar value to it. So it's dry. It's unsaturated, right? There's no excess pore pressure. All right, so let's rerun this analysis. And if everything goes well, the factor of safety should be quite a bit lower now because we're using the unconsolidated strength, or the strength that's in situ, consolidated under just the initial weight of the clay. Okay, and we are getting a much lower strength factor of safety, 0.762. So we need to move this grid a little bit to really capture the true failure mechanism. I don't think we have to move it a whole lot. Yeah, so 0.762, it didn't really change the factor of safety. So we've gone from a condition where we would have decided this is fine, we can build the entire embankment, now to saying, oh shoot, we can't build the entire embankment all at once. We're going to have to build it in stages instead, just based on one setting in the program. And now if we look at the shear strength, we see that it's constant, right? So we've got the same shear strength everywhere. And let's see, the shear strength right at the surface should be 5 kPa because I set that A parameter to be 5. So I'm not exactly sure why. It looks like it's more like down at around 0 to 1, which is a little strange. Let me make sure that I set that properly. Yeah, it should be 5 kPa when the effective stress is 0. So anyway, I'm not sure why that looks like that, but we've done the analysis correctly at this point, and we have got the right strength. So let's say that we wanted to know how much load we could apply, right? We know that we can't build the entire levee. Well, what we can do is move this down. I'm going to move it at -6, -3. So do 1 meter first at 6, -3. Let's try 1 meter. See if we can build that much. Okay, I think the factor of safety was over 2, right? So definitely we can build 1 meter. We could probably build 2 meters. So let's try and move it up at 2, 1. And then at -2, 1. Okay, let's try this one. And technically this fill should have some depth of cracking too, because it does have 1 kPa of consolidation stress. So here's a good amount of fill to add, right? We can do 2 meters of embankment. So let's build half of it first. Okay, now we've determined that we have 1.128. We want to make sure that the clay will be able to handle the next increment once it's fully consolidated, right? So what we can do now is come in and I'm going to move this external boundary back up to where it was before. Okay, that's what the original levee looked like. And now I'm going to come in and sketch a new material boundary. We'll go straight across and then up to here and over. And now I'm going to do material 3. Okay, and so if we wanted to analyze the condition after stage 1 has been added and the clay has come into and it's consolidated fully under the weight of stage 1, and now we've added stage 2, what we want to do is take away the stage 1 generating excess pore pressure. So we'll go to material properties, unclick this box for the sand fill. Let's do sand fill stage 1. Okay, and then material 3 is going to be sand fill stage 2. Okay, same properties, but this does create excess pore pressure, right? So now the material will be consolidated under this load, and this load will be generating excess pore pressure, and we can test this out. Okay, and we're at 1.139. So this looks like a good case where we would have to build this embankment in 2 stages, right? And we would wait for it to consolidate under stage 1 before doing stage 2. And if we want to look at undrained strength now, it is a bit higher, right? Because we've waited for stage 1 to consolidate the clay, and it's gotten stronger as a result. So that's the way that I would recommend to use a program like Slide to do analysis of staged construction. Now, one thing is missing, though, right? After stage 1 was added, we've assumed that it's completely consolidated, that there's no excess pore pressure left after stage 1 was built. In reality, we might want to add stage 2 before the consolidation is all the way done. And there's no way in this program right now to conveniently do that. So we would have to go back to some kind of analysis where we're doing zones, and we would have horizontal and vertical zones, and it would get really fairly complicated. So this is only assuming either that it's not consolidated yet under the weight by checking the box that the material above it does create excess pore pressure, or fully consolidated under that weight by checking the box that it does not generate excess pore pressure. There's no way to do a transient seepage analysis, a consolidation analysis yet. I think someday that may come, but it's pretty complicated, so it's just not quite ready yet.